In the early days of the coronavirus, you often saw headlines like these that highlighted how cases of COVID-19 were experiencing exponential growth. In this video, what I want to do is describe what exponential growth is and why there's a sense of concern around it. What I have here is a Desmos graphing calculator that I've set up to show different types of growth. And for right now, I'm not showing exponential growth. I'm actually showing linear growth. Imagine that I'm bicycling and every day I bicycle 6 miles. So after one day, I've traveled 6 miles, and after 2 days, I've traveled 12, and after 3 days, I've traveled 18, and so on. This isn't exponential growth. This is linear growth. And I can see that when I drag this slider back and forth, for example, to look at between days 6 and 7. On day 6, I've biked a total of 36 miles. On day 7, I've biked a total of 42 miles. The difference between those two numbers is 6. And that's true no matter how I move this slider back and forth. The day-to-day change, when measured by subtraction, is always the same. And if I want to move forward in time, all I have to do is for every day, add 6 miles. Okay, here's a different graph. And you don't know why it's exponential right now, but you can definitely see that it's not linear. It doesn't look like a line. And if I think about the differences here between, say, day 4 and 5 on how much bike riding has been done, it's a lot less than between days 8 and 9. When I subtract, those numbers change all the time. This is not linear growth. So why is it exponential growth? Well, what I'm going to do here is I'm going to change this equation. Instead of talking about subtraction, I'm going to change that to division. And now I want you to notice, it doesn't matter how I move my slider. The day-to-day change measured by division is always the same. That quotient is always 1 5/10. As I go from small change to big change, that quotient stays the same. And if I want to move from day to day, instead of adding a number, what I can do is multiply by this number right here. So to move from day 7 to day 8, I can multiply by 1 5/10. And then after I do that, I can multiply by 1 5/10 again and again and again. Here's that function showing exponential growth one more time. And what I've done is I've changed the x-axis and the y-axis. The x-axis goes out to about 30, and you can see the y-axis goes up to about 100,000, and you can tell the difference now that the graph looks really, really flat for the very beginning, and then it starts shooting up. This is typical of exponential growth. This is what you get when you keep on multiplying by 1 5/10, time after time after time after time. You get a function that looks small for a while and then really grows. So where do we see exponential growth? Well, this pattern of multiplying by the same number day after day or year after year, with small growth at the beginning and then large growth after that, can be seen in the world population, as we go back thousands of years to the billions of people we have now. It can be seen in the Dow Jones, shown here without accounting for inflation, starting from a low value to a very high value. Here's an example of what exponential growth looks like on computer chips. There's something called Moore's Law that talks about the amount of computing power on chips from year to year. And finally, here we see the total number of COVID-19 cases in the early portion of the epidemic. That's a good example of something that can be modeled using exponential growth. And that's why there is so much concern. Exponential growth, if it continues unchecked, grows at a tremendous rate. Thanks for watching. If you'd like to play with that Desmos graphing calculator, there's a link in the description. And if you want to learn more about exponential growth, I would strongly suggest Googling grains on a chessboard. There are lots of interesting examples that'll show how exponential growth grows very, very quickly.